Let's start with the geometry node. Then I'm going to start with a box. So this is going to be my wall, the basic shape of my wall. I'm going to move this box so it's on the ground. So right now it's in the middle. Let me change this color so it's easier to see. So it's right in the middle. It's not on the zero. It's not on the zero axis of the y. It's not the 0 point of the y axis. So I'm going to move this onto the ground plane. So this should be like 0.5. Because the default box puts it right smack in the middle of the grid. And it gives you a default box size of 1 by 1 by 1. So by moving it half the Houdini unit, which is half a meter, on the y-axis up, we'll put it smack on the plane, on the ground plane. I'm gonna start making the general shape of the wall. Let's try this. Let's pull it out. Okay, and then I want it higher. Okay, I want this more wider, around there. So let's say 4 by 2, a 4 by 2 wall. And I want it thinner. I don't want the wall that thick. So 0.5. Or actually even thinner. Too thin. 0.35. I think that's okay. So this wall is 4 by 2 meters. It's 0.35 meters thick. So when you're creating your wall, try to keep it above 1 Houdini unit. That way, there's less tweaking you'll have to do in the Dopnet, in the simulation. Most of the simulation parameters are aimed in meters, so above 1 or more. When you get less than 1, you have to tweak the parameters a lot in order to get the simulation to do what you want. I'm actually going to make this even bigger. I'm going to make it twice as big. This should be nice. So now we have the general shape of our wall. Cool. Now we can start fracturing it. I'm going to throw down an ISO offset. Well, this will turn it into the wall into a volume. So we have a volume right here. The purpose of doing this is so that we can scatter points in the inside of the wall. So there's about 1,000 points here. I'm going to lower this simply because I'm recording. I'll start to increase this scatter size a little bit more as I go into the simulation. Put down a good old Voronoi fracture. Now what this will do, it will fracture our wall for us according to these reference scatter points. These points. So these points are where we want the fractured pieces of the wall to be. So we're going to hook this up to the second input of the Voronoi fracture, and it'll automatically create these fractured points. In order to view these fractured pieces, we can throw down an exploded view to get a better look at it, but this is only going to be used just for debugging. We're not going to be using this, so I'm going to color it black. So this gives us a better look, this gives us a better visual of our fractured pieces. So you can size this, so you can adjust how you want to see these pieces. Okay, let's go back here. Smooth this up a bit. Now the Voronoi fracture has two outputs. One, it'll output the fractured geometry. So let's put a null right here. Out, fractured geo. Now the second output of the Voronoi fracture is the constraint geometry. This constraint geometry will tell Houdini. Now the Voronoi fracture has two outputs. The second output is the constraint geometry. So the constraint geometry will tell Houdini how to glue the pieces, or how to keep the fractured pieces together in a certain way of a certain strength. So when you have a collision done in the simulation, in our destruction simulation, it won't fall apart as easily, and it'll fall apart in a certain way that will be more visually appealing, depending on what kind of effect that you're looking for. So let's put a null here. Let's look at what the constraints look like. Now this is all this wireframe should look familiar to you if you've seen one of my previous videos on Vellum, and how how Vellum has constraints defining how the Vellum cloth or the Vellum geometry will bend and twist and stretch. You'll start to see a pattern with Houdini and how the constraints are defined. So let's take a look at the geometry spreadsheet here. We have this wireframe. Now there's points. That makes sense because this wireframe is a geometry. We have primitives. It's still geometry. The constraints are defined with rest lengths. They have rest lengths, which is how the length of each primitive. Now, let's take a look here. I'm going to isolate one of these pieces to show you how the constraints are formed by the Voronoi fracture. I'm going to come here to this cursor, press this, select 3D connected geometry. So I'm going to pick one piece. That's why I need this. I'm going to pick a piece in a corner. Let's take this big piece. So click this. While the cursor is hovering over the 3D viewport, press tab, type blast, because I want to isolate that piece. And I'll create this blast node over here. Select this, delete non-selected, untoggle this template. There you go. So this is the one piece that we have. I'm going to put a template on this, and I'm going to look at the constraint. You look carefully at the constraint. The dot right here, let me see if I can make this a little larger. So this dot right here, this point that's part of the constraint is right in the middle of this piece. And there's another dot here. Well, this is the piece in the other corner, right beside it, the neighboring piece. If we come back here. So let me isolate both of these pieces to get a better look. Press this cursor again. 3D connected geometry. I'm going to select this piece and this piece. And it'll create another blast here. This is one piece. This is two pieces. So over here. Okay. Delete non-selected. That's what I forgot. Okay. You can see this dot here is right in the center of this piece, of this larger piece. The other dot over here is in the center of this other smaller piece that we have isolated. You can see it's in the center. There, okay, that's a little better. So it's right smack in the middle. It's the centroid. Voronoi fracture is generating these constraints is by taking the centroid of every single fractured piece and connecting them together with neighboring pieces. So all the neighboring pieces, it's connecting all the centroids of every single piece and their neighbors. And it creates this network of a wireframe network sort of thing. Defines how the fractured pieces of the wall is connected together. That way we can use this to define the glue of our constraints and define how we want the pieces to stay together until a collision, something hits it hard enough to break the glue constraints that we defined here. And when that happens, the fractured pieces will start to fall apart in the destruction simulation. And depending on the strengths of the glue, and define how it'll break. The constraints that come out of the Voronoi fracture isn't something we can plug right into our .NET for our destruction simulation. It isn't something usable right out of the box. We need to name every single constraint so the solver will recognize what the glue constraints are and apply the necessary calculations in the simulation. We have to name every single constraint, every single line that we have here. So let me click this, go to the spreadsheet. It already comes with a rest length. Every primitive of this constraint That means every line, every white line here comes with a rest length. We also need a constraint name. So let's drop down an attribute create. Now there's something that's going to be called constraint underscore name. This will allow Houdini to recognize the glue constraints. So the class is a primitive. Type will be a string. So we're going to give it a name. It could be like glue. I type glue here. Put this attribute create above the constraints null. Simply because we need to name the constraints before feeding it into the Dopnet. And the out fractured constraint null node will be the one we feed into the Dopnet. Okay, let's go back up. Call this wall. I'm going to call it fractured wall. Okay, I'm going to drop down another geometry node. And this is where the simulation will be. So I'll call it sim. But I'm going to untoggle the render flag on the simulation simply because I'm not going to be rendering this simulation. I'm going to be rendering this fractured wall. Now, you've seen my previous video on destruction. You know that the simulation is only used to calculate the collisions of the fractured wall. And then after the simulation does all the calculations, we extract all that data with the Dop Import node back into this fractured wall geometry. So that way it's more organized. So you know where to find things. Fractured wall pieces go into the fractured wall. And the simulation is simply there to calculate the simulation. So let's go into the simulation. And let's drop down in Dopnet. Let's go inside the Dopnet. Now this is going to be a destruction simulation. So I'm going to need an RBD fractured object. So that's this right here. Then I need the respective solver. So we have quite a few. So it's going to be RBD solver or a rigid body solver. I'm going to stick with the rigid body solver. Simply because the rigid body solver gives me a number of substeps. By increasing the number of substeps, it will tell the rigid body solver to calculate the simulation with higher precision, but it comes with a cost. The more substeps you have, the longer it will take to cook the simulation, so please use this wisely. So that's something we can adjust. Now let's put down a gravity, and let's hook this all up. So we have to define what the RBD fractured object is. Right here, it has a soft path. Let's go back up to the simulation. Now, if you've seen any of my previous videos, you'll know that I like to bring in the geometry into this sim context and then bring it into the Dopnet. This way I find it a little more organized, but you don't have to do this. This is only just something I do. So I'm going to drop down an object merge. This is going to be the fractured wall. So I'm going to come here and look for this under this fractured wall. That's our wall that we defined. And that's the geometry right here. I'm going to go geo because we're going to have to import both the geo and the constraints. This way, and then put down null. I'm going to copy this. This is going to be my constraints. So this fractured wall. So let's come here. It's going to be this one, the constraints. So let's go back into the Dopnet. RBD fractured object. Okay, I wanted to just show you this fractured geometry, wall geometry. So let's see what it is. I'm just going to go here. I'll take us right to it. So that's these two nodes that I have imported. Let me color it blue. So that's these two nodes here. The fractured geometry node and the fractured constraints node. These two datas I've just pulled over and imported it into this simulation context like this. So this is just for easier access. You don't have to import it over into this context. You can actually define, link it right into the Dopnet. So let's go inside the Dopnet. In this RBD fractured object, the soft path, I can now easily, I'm just gonna close this, collapse that. This fractured wall, I can just click this. This would be using the original fractured geometry. This is our original geometry. You can just link it right like that. However, since I had imported it into the simulation context over here, I can easily get everything right here. So now it's available right here. Out fractured wall geometry. I can choose it like that. And right after you pick the right SOP path, you'll notice that in the 3D viewport, it updates. You'll see that our fractured geometry is available here. So I'm going to turn off these points because they're rather big. Okay, since we have something going, let's just play it and see what happens. Okay, it's falling, so it's doing something. Now it's not hitting anything because one, we don't have a ground plane, we don't have anything. So that's one of the first things let's add, a ground plane. Drop down and merge to merge the ground plane into this simulation setup. Let's drop down a ground plane. Now the ground plane is a static object. It needs to be merged from left to right. So this crisscross is no good. Select the merge node, move the ground plane up. So now we don't have this crisscross. It's merged. The ground plane is merged left to right. Now let's replay the simulation. Okay, now we're getting these fractured pieces successfully hitting the ground, colliding with the ground. So we're getting close, we're getting there. However, as you can see, this fractured wall is falling apart immediately. Like there's nothing holding it together, there's nothing gluing it together. Right when we start the simulation, it fractures immediately. It's not holding together. We're not using the glue constraints that we have defined earlier. Let's move this up a bit. There's something called a constraints network. So that's this right down here, the constraint network inside of our Dopnet, and that will help us define how these fractured pieces are held together. So let's drop this down. Now it has 3 inputs, objects to be processed, constraints to create, and a third one, constraint solvers. But we're not going to be using the constraint solver in this video. Objects to be processed. Now that's this RBD fract, but we don't hook this up. We don't necessarily hook this RBD fractured object up. We hook it up down here from after the merge, after the last merge node. We hook this down here. And then the output goes into the output. Now it's still giving us an error because we haven't hooked up the constraints yet. So let's see what the error is. So if not enough sources specified, simply because we don't have this constraint hooked up yet. So there's also something called, now I'm going to type in relationship. And I'll list all the relationship nodes. The one that we want, the one that I'm going to show off first is the glue constraint relationship. So let's hook this glue constraint relationship into the second input of the constraint network, and the error goes away. Now let's select the constraint network. It's asking for a SOP path. The tooltip says the SOP geometry to use to determine the constraint. If you remember from before, when we let me go back here. So this is our original network, original wall. That's this guy. If I put the render flag on the out fractured constraints, that's this wireframe. And this wireframe are primitives. This is an actual geometry. So these are primitives. This constraint is actually primitive. It's actually geometry. So let's go back to the sim. Let's go into the Dopnet. Constraint network. SOP path. Tooltip says the SOP geometry to use to determine the constraints. So we know what that is. So let's choose this. Under the sim, because I had imported all the wall geometry into the sim contacts, so I can easily get it from here. So that's this guy, this fractured wall constraint. Now, nothing's happening, okay? Let's go to the glue constraint relationship. So in here, we have to define which constraint to use. Now that's the glue name that we used. Let's go back up all the way to the fractured wall. That's this attribute that we created right here. That's this right here, this glue name. Let's go back to the sim, glue constraint relationship. So let's type in for the data name, that'd be glue. You might be thinking, still nothing is coming up. Well, let's put a wireframe view. Let's, hide other objects and then wireframe. There it is. The red lines is representing the glue constraint relationship. Now, if you wanted a different color, you can come here in the glue constraint relationship, the guide options, the color, you can change it to any color you want. Green, blue, red, orange, yellow, white. White is not very useful because everything else is white. So, okay, let's stick with red. Let's just try and play it. Now, as you can see, some of the red lines are disappearing. Let me drag the play head a little back. See, right here, when we start to play the simulation, these red lines are disappearing. Some of them, not all of them. The red lines represent our glue constraints. As we play the simulation forward, we see the red lines start to disappear. As the red lines disappear, the glue constraints are being broken. And in this case, the force of the gravity is the one acting on our fractured wall and breaking the glue constraints that we have set up here. Now let's try something. I'm gonna ignore the gravity and then reset the simulation, play it again. See if it still happens. Now the red wire frame lines are not disappearing. That's because there's no forces acting on this fractured wall. So when I put the gravity back into the simulation, you'll notice that force is applied. Gravity is a force. It's applied onto this fractured wall. And that causes these glue constraints to be broken. And when they break, these red lines will disappear. So we can use this to debug our destruction simulations and use this for feedback when tweaking the glue strength or glue parameters to get the visual effect that we want. So I'm going to put the gravity back in and reset the timeline. I'm going to increase the glue strength. Let me triple the strength. So we have 30,000 for the strength, for the glue relationship strength. Let's play it. So the glue constraints, the red lines are not disappearing anymore. The strength of the glue defines how well these pieces are being glued together, how well they're being held together in place. The gravity, right now, the gravity is not strong enough to break any of the pieces, any of the glue constraints at all, because we have increased the strength of the glue. So this setup is not very interesting. There's nothing hitting it. So let's create a collider geometry to collide against this wall. And things will get a little bit more interesting. Turn this back to flat wire shaded. Let's go up. Create another geometry node. Drop down a spear. I'm gonna have a ball just hit against it. Oh, I'm gonna ghost it so I know where to position the ball. Come back up here to the fractured wall. I'm gonna put the render flag on the fractured geometry so I have a better look at the positioning. Come back up. Here's spear. Now this spear, I'm gonna turn it into a polygon. Let me increase the frequency just a little bit so it's more smoother, so we get a more smoother ball. Transform. I'm gonna move this ball a little back. Wrong one. This one, move it, here. Let's say 10 meters back. Okay. And I want to position it, position them out. Right now the ball is right in the middle of the ground plane. So if we were to simulate this, the ball is going to be colliding with the ground plane. So let's move the ball up a bit. Let's say 2 meters maybe? 2 meters, maybe 1.5. Okay, 2 meters should be good. Okay, I'm gonna put a null out. Geo. Let's go back up. Let's go into the simulation. Go into the .NET. So we need to add our ball into this destruction simulation because the sphere is a rigid body object. So we need an RBD. And it's not a fractured object, so we're not going to use this one. We need an RBD object. Okay, now how do we hook this up together? There's only one input. We can merge it. I'm going to merge this down here, merge the RBD fractured here, and then hook this up to the first input of the rigid body solver right here. So right when we hook that up, you'll see that there's a ball that appears right here in the 3D viewport. Now I need you to note that this ball is not the ball that we added. If you look carefully. This ball doesn't have a lot of, let's see, yeah. This ball doesn't have a lot of geometry. If, go back, look at our own ball. This ball. Now this ball has a lot more geometry. And it's also positioned further away from the wall. Away from the wall. There's a bit of space between the wall and the ball. Now this is our ball that we created. In the sim geometry, in the Dopnet, this RBD object is the default geometry that comes with it. So it loads a default ball for us. However, I don't want to use this one. I want to use my own. You can use this one if you want. But I want to use the one that I created. So I'm going to, come up here. And I like to bring everything into this context again. So I'm going to drop down object merge. Name it ball geo. I'm going to select this. Now this will be the ball. So that's this context down here. Out geometry. Give it a nice name. Okay, let's go back to the Dopnet. The RBD object. Salt path. I'm going to choose that in the sim, so I can collapse this. In the sim context, now that we brought all the geometry into here, is this out ball geometry that we need. And look, it bounces, it places itself right in the correct spot. I'm going to put the render flag back to the output. Now let's just play it. There's no harm in just trying it out. So the ball is hitting the ground, which is nice. It's colliding, it's doing the right thing. It's working. However, we want the ball to hit the wall. We want it to give the ball a bit of thrust. We want it to give it a bit of velocity. Select the RBD object, and we can, under the initial state tab, velocity, we can give it some initial thrust or initial velocity to get it going. So let's give it -20. And let's just play it. Okay, so it's heading in the right direction. And look, our wall is fracturing. Velocity to give it that impact to break part of the wall. And the wall's not falling apart completely. It's falling apart slowly. Let's rewind this. Let's make the strength of the glue a little less. Let's give it like 20. Let's play it. Oh, now it breaks a bit more easier. Now I'm going to replay this simulation with wireframe, and I want to look at these red lines and how they disappear as the ball collides with the wall. So right when the ball hits it, all these pieces right in the middle, all these wireframes, they disappear. The red lines disappearing and the glue constraints start breaking, which is both caused by the impact of the collision. The impact of the ball and the wall results in a big hole in the middle, cracking the wall down right in half. Now there's a lot of cool things we can do with this. In the glue constraint relationship, not only we have a strength, we have a half-life, we have a propagation rate, and a propagation iterations parameter. Now this one is quite interesting, but in order to illustrate this parameter, the use of this parameter, I will probably need more pieces. I'm going to create a shortcut. In here, I'm going to type in a null, drop this down. I'm going to call it params. So this is going to be a shortcut where I can define the number of pieces for my fractured wall. I'm going to create a nice parameter shortcut here, so I don't have to flip back and forth from the Dopnet and into the geometry context. So for this null, select the null, come up here to this gear wheel, click it, edit parameter interface. I'm going to create a new UI for this. What do I want? I want an integer because I want to define how many pieces. So I'm going to select the integer, drag it over to the root and drop it down. Now we can fill in what the name is. I'm going to call it total pieces. And for the label, it's going to be total pieces as well. I'm going to apply this. I'm going to keep this window open though. Now we have to link this parameter. So look over here. This null is now updated. this parameter window has now been updated with this total pieces field. So we have a new field here. This field is not linked to anything yet. So let's go back over to let's go back up all the way to the object level, and in the fractured wall, now that's what we want. So this scatter node defines how many pieces gets fractured out of this wall. Now I want to easily change this parameter value inside the Dopnet. So I want to link it to this total pieces UI that I create, this field that I've created. So come over here, select this total pieces, and then come over to the channels tab over here, and you'll see add links. Drop parameters here to add new links. So I'm going to come over here to the scatter node, force total count. Click this and drag it over and drop it into here. And you'll see that this link field update. So I'm going to click apply, and you'll immediately see this force total count jumps to 0. That's because our default value for this is 0. Now let's just accept this because I don't need that window anymore. Let's go back up. Let's go to the simulation, Dopnet, and in our params, so this total piece is 0. I'm going to change this to 100. No, I'm going to change it to 200. And then I'm going to press enter. Now immediately you'll see in the 3D viewport that our fractured wall updates with more pieces. Now let me select this null here, right click, go to parameter and channels, go to parameters. Click this. Now this is just so I can have a floating window right here. And I want to show you when we go back up to the object level, back to the fractured wall again, this scatter node, I'm actually going to give it a different color. I'm going to give it green, just to indicate that we have a linked parameter in this scattered node. Now, this is 200, and the force total count is 200. So if I increase this to 300, look what happens here. The force total count goes to 300 as well. And now this fractured wall. Okay, so let's go back up to the simulation. So now that we have an easy shortcut into configuring our wall without jumping back and forth, that was the whole purpose of that, I can slowly increase the number of pieces so we can have a more interesting effect. This parameter, I'm going to change this to 500, and you'll see more pieces. Okay, I'm going to choose 700. Okay, and I want to try the simulation. I want to test this out, if my computer can handle all these points. Well, it seems okay. It runs pretty smooth. Okay. Now that we have smaller pieces, we have a more, its impact, the impact of the wall is more of a circle shape in the middle here. You can see that the impact is more limited to where the colliding area is. So you see this big hole here. I want to show you what this propagation iteration does. I'm going to give it a value of 100. What this should do is should spread the impact force, the impact of the spear, of the impact of the ball hitting the wall. That impact will now spread. It'll spread all over the wall. So that's what this propagation iteration spread out further, so it'll break more easily. I've increased the propagation iterations to 100. So let's see what happens when we recook the simulation. Now the whole wall sort of breaks apart. Let's see what it looks like in wireframe so we can look at the constraints and see how it breaks apart. So it breaks apart almost immediately. So right when it hits, all the constraints break. So this propagation is probably too much. Let's try 10 and let's reset this. Okay, that's a bit better. No, we have a bigger hole now. So let's increase the size of the hole. Now I'm going to reset this. I'm going to let's see if I can handle 1,000 pieces. Glue constraint, let's give it 100. And then redo this. Okay, that's propagation is way too much. Let's keep it at 10. Let me ignore the gravity so I can isolate just the propagation iteration and the so I can isolate one thing at a time. I don't want the gravity sort of debug the simulation slowly, one force at a time. Well, that's a nice effect. So without gravity getting in the way, I really like this break. So without the gravity dragging down the pieces, the impact of the collision looks much more powerful. That tells me in order to get the effect that I'm looking for, I need to lower the gravity force. Let me put the gravity back in. However, I'm going to make the gravity a lot. I'm going to half the gravity. Divide the gravity in half. Divide the force of the gravity in half. So let's redo this. No, it's still too strong. Gravity's still too strong. Let's divide it by 3. Now say this is, we're happy with this. Let's go back up. Let's go back up to the object. I'm gonna finish up the setup of the scene, and then I'll show you different ways of setting up the constraints. So hide other objects. So right now, if I were to render this, it wouldn't render properly, simply because this simulation, you can't really render the stuff that comes out of the simulation. You have to extract the data from the simulation in order to render it. So let's go back up to the fractured wall. What we need to do is add a Dop Import node. Okay, so if I put Dop, we have several Dop imports. This is the one where I'm going to use Dop Import. Drop this down. What this will do, it will extract the data from the Dopnet into this context. Let me put the render flag here. So the Dop network, that's the Dopnet that we had before. So let's go here. In the sim context, the Dopnet, that's this. Set that there. Import style, transform, fetch geometry from Dop network. That's what we want. So everything comes up here. However, I just want the wall. So let's go back up. Go into the simulation. Go into the Dopnet. Oh, actually, we don't have to go here. Just select this Dopnet. Open up the geometry spreadsheet. And you'll see all these pieces. Now that's the fractured wall. That's the fractured wall pieces. We need to import this. I'm going to import all these fractured pieces. Let's go back up, go to the fractured wall, and go to the Dop Import. Now for object mass, I just want the pieces. So right now, it's giving me the ball, it's giving me the ground, it's giving me everything. I just want the fractured wall. So I'm going to go piece, and then asterisk, because every piece has a different name. There's piece 0, 1, piece 0, piece 1, piece 2, piece 3. So piece asterisk is a wildcard. It'll match all the numbers. So this gives us just the fractured wall. So if I move this playhead back and forth, you can see it fracturing. But we don't see the ground, we don't see the ball. That's all right. So we can add a null here, and this can be rendered. I'm gonna call it out rendered. Now let's go back up. Let's go to the ball. The same thing we did with the fractured wall, we have to do for the ball as well. We have to extract velocity and all the animation data from the simulation into this ball context. So we need the same thing. We need the Dop Import, this Dop Import field, a node. Drop this down, put the render flag on the Dop Import, and for the Dop network, well, that's going to be the same one. In the sim context, the Dopnet. That's that node. Import style, fetch geometry from Dopnet. Now this, again, brings us everything. We just want the ball. So let's go back up. Let's go into the sim. Let's select the Dopnet, and let's see what it's called. Now there's a lot of pieces here, and you might be scrolling. You might be having a hard time finding that ball because of all the pieces in the way. Now let's go into the Dopnet. The ball is this RBD object. Now the ball was our RBD object. So if we now scroll down, let's look for the RBD object. It's right on the bottom, right here. There we go. this RBD object. It's right on the bottom. So you can actually just copy this name, go back up, go to the ball, go to this Dop Import. For the object mask, just paste it in RBD object 1. And that's this ball. And if we move the playhead, we'll notice that it's actually moving. And this is ready for rendering. Remember to put the render flag on this node. Now we have both of them rendering properly. However, we don't have a ground. Now we can always add that. You don't really need this. If you're okay with the simulation without a ground rendering, that's fine. You can add it in. So let's go back in. Now for the ground, we don't really need to import the ground from the simulation, simply because this ground is just like, okay, this ground is not worth rendering. This is really not worth rendering. All you had to do, okay, let me place the tall render flag back here. In the ground, all you had to do is just put a grid down and just make it really big. Make this like really big. Put the null out render. So it's always good practice to put this out render node here and place the render flag here. Come back up. So we have everything rendering in a good rendering spot. And it's nice and organized as well. So if you didn't want to render the ground, you could just untoggle it right on this context. If you don't want to see the ball, just untoggle this and it's gone. So we have this all set up now. Now let me put the render flags back here. Let's go back to the fractured wall. It's extracting data from the simulation. However, it'd be nice if we put a file cache here. So after, I mean, you don't want to keep cooking the simulation over and over and over. After you're done with your simulation and you're happy with it, it's a good idea to put down a file cache so the simulation can load faster. Now put down this file cache. I'm going to call this fracturing wall. And for this file cache, I'm going to remove the hip name simply because I have many versions of the hip file. You can keep that in. It's just something I do. Now, I need the $F. So the $F has to be there because every single frame, the wall, the fracturing wall, the pieces are fracturing. They're moving for every single frame. So you need that there. Check the load from disk. And after you're done that, click the save to disk button. So we have this all cooked out, and so this runs a lot faster. It's more optimized that way. So again, I'm going to do the same thing for the ball as well. Let's go back to the ball, down here, throw down a file cache. Oops. I'm going to remove the hip name again. And again, you can keep that in there. It's only something I do. Check the load from disk, save it. So the ball saved a lot faster because it's not really doing much. This video covered the basics of setting up a destruction simulation using glue constraints provided by the Voronoi fracture, and I covered some basic concepts for glue constraints to understand some fundamentals. In the next video, I'll go over how to create glue constraints from scratch without using the Voronoi fracture. This is important because you may not always have the convenience of the Voronoi fracture to provide out-of-the-box glue constraints ready for plug and play. What if you wanted to build a structure from bottom up, say brick by brick or piece by piece? That's where the next video comes in. I demonstrate building a simple wall by stacking boxes together and manually creating the glue constraints from scratch without the use of the Voronoi fracture. Please check out the next video on manually creating glue constraints from scratch. Links in the description. Thank you for watching and sticking to the end.